Welcome to lecture 27, which is dedicated to the Taylor formula. Now, the Taylor formula is the answer to the following problem. Given a function f of x and a natural number n except 0, find a polynomial P n of x such that. So this polynomial has the following two properties. The degree of P n of x has to be less than or equal to n, and the function f of x can be approximated by the polynomial Pn of x, and in this approximation we make an error which is little o of x to the n for x that goes to 0. Now, this last equality is what we call the Taylor formula with Peano remainder and what this formula says basically is that we are now approximating the function f of x with a polynomial, and as you may guess, this is a very important possibility that we have now, because whatever f of x we are given, we can replace the function f of x with a polynomial. So this will be an important tool, for example, for solving limits. Now, let's say something else about the remainder. So the remainder is the error in approximating f of x with p n of x. So in other words, we can say that f of x minus p n of x, which is just the error, this error has to be little o of x to the n. Good. So before giving the explicit formula for the polynomial, we want to prove an important property, which is the uniqueness. Okay, so we'll give this lemma now. If f of x can be approximated by a Taylor polynomial Pn of x, this polynomial is unique. So we are saying that if it is possible to determine a polynomial Pn of x that satisfies the two properties, namely the fact that the degree of polynomial is less than or equal to a given number n, and f of x can be expressed as the polynomial plus a remainder which goes to 0 faster than x to the n, then this polynomial is unique. So let's provide a proof of this, and this proof will be by contradiction. So let's assume that there exist two Taylor polynomials let's say Pn of x and Qn of x, right? So, well, if these two polynomials are Taylor polynomials, well, that implies that, for example, the degree of Pn of x is less than or equal to n, and f of x is equal to Pn of x plus little o of x to the n. Of course, this is true for x that goes to 0, right? Well, the same thing can be said also for Qn of x. So the degree of Qn of x should be less than or equal to n, and f of x can be expressed as Qn of x plus little o of x to the n for x that goes to 0. Good, so we have these two properties. Now, with these two properties, we can also say that if we take the difference of these two expressions, right? So this expression and this expression, what we get is that Pn of x minus Qn of x, well, this of course is going to be a new polynomial, and certainly this new polynomial, the difference of Pn and Qn, well, this polynomial would have a degree which is less than or equal to n. This must be, of course, right? Because there will be nowhere any powers of x larger than or larger than n. So the difference clearly will contain only powers of x less than or equal to n. But also, we can also say that Pn of x minus Qn of x, well, this will be little o of x to the n, and this can be easily seen by just looking at the properties of little o of x to the n. Now, let's consider these two propositions together. And well, if we consider these two propositions together, I want to prove now that this implies that the only possibility is that Pn of x is exactly the same as Qn of x, which means these two polynomials are identically equal. So for every possible x, they are exactly the same polynomial. They take exactly the same value. Okay, so why is that? Let me prove this final fact. Now, Pn of x minus Qn of x, this polynomial, we said that this polynomial will contain powers of x up to n. Okay, so it will have, in general, it will have, we'll start from ak x to the k, plus there will be ak plus 1 x to the k plus 1 up dot dot dot. Well, the last possible term would be an x to the n, right? This is because the degree would be less than or equal to n. We don't know if k starts from 0. So let's say that k is in general something that can be less than or equal to n, because it is possible that the only term that will survive after subtracting one from the other would be just the nth term. But in general, this is the shape, right? So this is basically just derived by using the property A, right? So from property A, we know this. But from property B, we can also, well, we should check that this difference between polynomials is little o of x to the n, which implies that the limit as x goes to 0, right, of Pn of x minus Qn of x divided by x to the n well, this limit should be equal to 0, right? So let's see what that implies. This is the limit as x goes to 0. We have x to the n here, and there will be a k x to the k plus a k plus 1 x to the k plus 1 plus dot 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 a n x to the n. Alright? Well, now we know that k is less than or equal to n, right? So we can also rewrite this as the limit as x that goes to 0 of, there will be a first term, ak x to the k divided by x to the n, which, I mean, by just using the properties of powers with the same base, we can also rewrite this as just simply 1 divided by n minus k, and plus all the other limits. But we immediately see that no matter what the other limits will do, this limit will be clearly plus infinity, right? Well, it will be plus or minus infinity depending on the sign of ak, but what really matters now is that this is clearly right. So we can assume that this limit represent only the limit of this fraction, right? And but suppose that ak is equal to 0, then the next term is gonna be limit as x goes to 0 of ak plus 1, and there will be 1 divided by x to the n minus k minus 1, right? And again, because this may or may not exist depending on ak plus 1, but if this exists, this will go to plus infinity. So you see that the only possibility for having this limit to be equal to 0, okay, so the limit of Pn of x minus Qn of x divided by x to the n as x goes to 0 is equal to 0 if and only if ak is equal to ak plus 1 is equal to an is equal to 0, which is to say that basically this implies that Pn of x minus Qn of x is identically equal to 0, which implies that Pn of x is identically equal to Qn of x, which concludes the proof. Now that we know that the Taylor polynomial is unique, we are ready to give the polynomial, to explain how the polynomial is made. So, and we'll give this result in the form of a theorem. And this, we will only state the theorem, we'll prove the theorem much later. We need additional tools for proving the theorem. And this is only the sufficient condition. So let f be a function defined in a neighborhood of the origin. Basically that means from in an open interval minus r with values in r, and this for some r larger than 0, right? So we are referring now to a situation like this. We have 0 here, this is plus r, and this is minus r. Okay, so this is the interval where the function is defined. Let's suppose that n be a natural number without the origin, and let's check now that these two conditions are verified. First condition, we have at least the first n minus 1 derivatives, which are first derivative, second derivative, up to fn minus 1 derivative, they exist in the interval minus r. So the first condition is that this function has n minus 1 derivatives in the interval in the neighborhood of the origin between minus r and r. Then, of course, why am I saying at least? Because if the function has more derivatives, it's even better. But this is what we need, okay? And we also need that at least the nth derivative exists. Now, we are not requiring that the nth derivative exists in the entire neighborhood, but only in x equals 0 into the origin. So we are asking that the first n minus 1 derivatives exist in the entire neighborhood of the origin, but only the nth derivative exists in x equals 0. Again, if we have that the nth derivative exists in the entire interval, or if we have that even more derivatives exist, even better. Okay, but this is what we need. Then we can conclude the following thing. We can conclude that the polynomial Pn of x, which is the polynomial that we have defined right at the start, okay, the Taylor polynomial, can be is given by the function evaluated at 0. So this is the first term of degree 0. And the term of degree 1, what is the coefficient of the term with the powers with one exponent 1? Well, this would be the first derivative evaluated at the origin divided by 1 factorial. And the second, the coefficient of x to the square will be similar. It will be the second derivative evaluated at the origin divided by 2 factorial, up to the final term x to the n, and the coefficient will be the nth derivative evaluated at the origin divided by n factorial. Okay? Now, of course, this can be expressed here more compactly with the following expression. We can write this as a sum. K goes from 0 to n of f derivative of order k. We will represent the derivative in this way, with f with an exponent in parentheses where we put the number of the order of the derivative, evaluated at 0 divided by k factorial x to the k. And we are assuming now, so we will just convention. The convention is that f to the derivative of order 0 of x will be just the function itself. Okay, so this is the convention that we are using. Notice that first thing which might be worth noticing is that if we need to find the Taylor polynomial of order n plus 1, well, this would be can be calculated recursively from the Taylor polynomial of order n simply by adding the last term. And we know what the last term is going to be. It will be the term that contains the power with the exponent n plus 1, and the coefficient will have n plus 1 factorial at the denominator, and they will be the derivative of order n plus 1 evaluated at 0. Okay? Now that we know what is the general form of Taylor polynomial, let's provide some Taylor polynomials for elementary functions. And for the time being, we just provide the Taylor polynomials, and later on we will give the proof of these Taylor polynomials. So if we have the exponential e to the x, this can be expressed as in form of Taylor polynomials as 1 plus x plus 1 over 2 factorial x to the square plus 1 over 3 factorial x to the cube, and so on and so forth. And I'll remind what is the shape of the exponential. This is e to the x, and what we are saying is that we are approximating the function around the origin. Okay, so this will be basically the approximation of the exponential around the origin with a polynomial function. Next elementary function is the sine of x. Sine of x can be expanded in a Taylor polynomial as x minus 1 over 3 factorial x to the cube plus 1 over 5 factorial x to the fifth minus 1 over 7 factorial x to the 7, and so on and so forth. In the graph of the sinusoid, is something like this, and we are now again expanding the polynomial, the sine of x around the origin. So in a neighborhood of the origin, we are saying that this function can be approximated with this polynomial, and of course up to a degree that can change. Next function is the cosine of x, that becomes 1 minus 1 over 2 factorial x to the square plus 1 over 4 factorial x to the fourth minus 1 over 6 factorial x to the sixth, and so on and so forth. So you see that the sine of x polynomial contains only odd powers of x, and instead the cosine of x contains only even powers of x. The graph of the cosine of x is something like this, and we are saying that we are approximating this polynomial in the neighborhood of the origin. So we might think of a function like this. Let's now consider the logarithm of 1 plus x equal to x minus 1/2 x to the square plus 1/3 x to the cube minus 1/4 x to the fourth. So let's have a look at this function first. Okay, logarithm of 1 plus x is nothing else that the logarithm of x, which has been shifted to the left by 1 unit. So we see that now the logarithm will tend to minus infinity when x goes to minus 1. In fact, when x goes to minus 1, what happens is that the logarithm tend to be 10 of 1 plus x tends to the logarithm of
0, which is minus infinity. Okay, so this is why we have shifted the function to the left by 1 unit, and we see that the function now crossing at the origin of the coordinate axis when x is equal to 0. Now, we want to make an approximation of this function around the origin. So exactly in this neighborhood of the origin, what we have is that we can approximate the logarithmic function log to 1 plus x with some curve like this. So you see that the approximation is as good as we get closer to the origin. And this is just the approximation of the Taylor polynomial. Another function which we want to consider now is the arctangent of x. We see that the arctangent of x is this function that goes from minus pi over 2 to pi over 2, and it is another odd function, right? And we make an approximation of this function in this neighborhood of the origin, okay, where we are between minus r and r. We see that this function can be approximated by this blue curve, and again, the approximation is as good as we get closer to the origin. The final function that we want to consider now is the power 1 plus x raised to the alpha, which is alpha is any real number, can be positive, can be negative, any real number. So this function can be approximated by a Taylor polynomial as follows: 1 plus alpha x plus alpha times alpha minus 1 divided by 2 factorial x to the square plus alpha times alpha minus 1 alpha minus 2 divided by 3 factorial x to the cube, and so on and so forth. So clearly this is different depending on the value of alpha. We'll come back on each of these polynomials when we will give the proof of them. But notice something now. Notice that when dealing, for example, with the sine of x, which we know to be an odd function, in fact, we know that sine of minus x is minus sine of x, so this is clearly an odd function. And we notice that in the Taylor polynomial, we only have powers of x with odd exponents. So this seems to suggest that an odd function only has odd powers of x. If we go to another odd function, just like the arctangent of x, in fact, remember that the arctangent of minus x is equal to minus arctangent of x, so this is another odd function. Once again, we see that the Taylor polynomial only contains odd powers of x. If instead we consider an even function, just like the cosine, and we know that the cosine of minus x is equal to the cosine of x, confirming the fact that we are dealing with an even function. So this is an even function. Well, we see now that the Taylor polynomial only contains even powers of x. So we're led to generalize this result, saying that it is possible that for every function f of x which is even, the corresponding Taylor polynomial only contains even powers. Instead, it is possible that if f of x is odd, then the Taylor polynomial contains only odd powers of x. Now, this turns out to be true in general, and we will prove this. Okay, so let me first start the proof with the function f of x, which is even, right? So if we have an even function, well, that implies that the derivative of odd orders are odd function. Uh, think, for example, at the cosine, right? So if we have the cosine, we know that the first derivative, which is an odd derivative, is the sine. And the same happens for the third derivative, another sine. For the fifth derivative, another sine. So every odd derivative of an even function is an odd function. So we can say that f, the derivative of order 2k plus 1, and we see that 2k plus 1 of course is an odd number, well, the derivative of order 2k plus 1 of x is an odd function, but that implies that if we evaluate this odd derivative at 0, we get 0. But remember that in the Taylor polynomial, this is basically one element of the coefficient of the powers of x that has exponent 2k plus 1. So this implies that Pn of x can only contain even powers of x because all the odd powers would be multiplied by a derivative of odd orders evaluated at the origin, which would be 0, right? So this is just the proof of the first fact. Let's now go to the second part of this proposition. And the second part of the proposition is that f of x is odd. Then we want to prove that the Taylor polynomial of this function is contains only odd powers of x. Well, let's see. If f of x is odd, for example, think about the sine function. Well, if we so at this point we made some practice with the use of Taylor polynomials. It's time to prove all the Taylor polynomials of the elementary functions. So let's start the proofs, and let me start with the exponential. Remember that the exponential e of x can be expanded into 1 plus x plus 1 half x to the square plus 1 over 3 factorial x to the cube, so on and so forth. I'm writing here the general expression for Pn of x, which is sum, k goes from 0 to n of the kth derivative of the function evaluated at the origin divided by k factorial x to the k, right? So this is what we need to. Let's prove now the expansion for the function sine of x. And remember that by convention, the function is nothing else that basically the derivative order 0. If we take the derivative order 1 of x, we get cosine of x. The derivative order 2 of x is minus sine of x. The derivative order 3 of x is minus cosine of x. And notice that if we take the derivative of order 4 of x, we get sine of x. So in other terms, we are basically back to the start. So this says that we have a cycle, okay, of 4 possible derivatives which repeat themselves over and over again. So we just need to determine what are the values of these 4 derivatives at the origin. Notice that this derivative of order 0, which is just a function evaluated at 0, this would be the sine of 0 is 0, right? And the same thing happens for f of order 2, because that would be minus sine of 0, which is 0 again. So this is clearly an indication that f of any even order. Let's now prove the Taylor polynomial of f of x equal to the sine of x. Now, remember that by convention, f of x is nothing else than derivative of order 0. If instead we go with the derivative of order 1, we have cosine of x. The derivative of order 2, we get minus sine of x. The derivative of order 3, we get minus cosine of x. And if we have the derivative order 4, well, this turns out to be exactly equal to the function itself. So the derivative order 4 of x is equal to f0 of x. And now we see that we have a cycle that repeats itself because the derivative of order 5 of x is going to be cosine of x. Derivative of order 6 of x, we have minus sine of x. Derivative of order 7 of x, we have back again minus cosine of x. And of course, the same thing will repeat over and over modulo 4. Okay, so the only thing that we need to check is evaluate these 4 derivatives in the origin. Okay, now what we see here is that f0 evaluated at 0, because this is the sine of x, of course this is 0. And the same thing happens for f2 of 0, which is again minus sine of x, so this is 0. And we see that for every possible even derivative, we are back into some plus or minus sine of x that always gives 0. So we can conclude saying that f2k of 0 is equal to 0. And this is no surprise because we know that this will remove all possible even powers of x from the Taylor polynomial as expected, being sine of x an odd function. Let's see what happens with the other derivatives. We have that f of order 1 evaluated at 0. This is the cosine of x. So this is a totally similar proof can be given for the function f of x equal to uh, cosine of x. Okay, so we can say that the function is nothing else than derivative order 0. So we go at the derivative order 1, we get minus sine of x. The derivative of order 2 of x, we get minus cosine of x. The derivative of order 3 of x, we have sine of x. And if we go to the derivative of order 4, we are back to f0 of x. Okay, so this would be f4, this would be f5, this would be f6, this would be f7 of x, and again, right? So even in this situation, we see that we have a cycle of 4 derivatives that repeat themselves. So what we need to do now is just calculating the values of these 4 derivatives, right? So for the first derivative, we have that f, well, this is not actually a derivative, but the function itself evaluated at 0. And clearly, we see that we have a 1 for the f1 evaluated at 0. We get a 0 for f2 evaluated at 0, we get minus 1, and for f3 evaluated at 0, we get back again 0. So this time we see immediately that every... Right, so let's prove now the Taylor polynomial formula for the logarithm of 1 plus x. So we have f of x equal to the logarithm of 1 plus x. We know the convention, so this is the derivative of order 0. Now, if we go to the derivative of order 1 of x, using what we know about derivatives, this is simply 1 divided by 1 plus x. Then we have the derivative of order 2 of x, and this is simply minus 1 divided by 1 plus x to the square, and the derivative of order 3 of x. Remember that this can also be written as, let me use the green pen here. So this can also be written as minus 1 plus x raised to the minus 2. Excuse me. So the third derivative is basically 2 times 1 plus x to the third, okay, which can be also written as 2 times 1 plus x to the minus 3. So it will be easy then to write the fourth derivative as simply minus 2 times 3, 1 divided by 1 plus x to the fourth. So we see that we have a pattern, okay? So the possible generalization that we might think at this point is the following. We might think that the derivative of order k, right, of the function logarithm of 1 plus x, we notice that whenever we have, you see, a derivative of order 1, 3, we have a positive coefficient, right? So if we have an odd order of derivative, we have 1 as coefficient. Instead, if we have an even order of derivative, we get a minus. So the sign could be something like minus 1 raised to the k plus 1. So that shows that if k is odd, you get a 1. If k is even, you get a minus 1. So this seems to be reasonable, right? So then we have a fraction, and we see that we always have at the denominator a fraction, a power of 1 plus x, with an exponent which is exactly the order of derivative. So we might think that this is raised to the k. And another thing that we notice that basically at the numerator, we may have the factorial up to the integer before the order of derivative. So we might think that this is k minus 1 factorial, okay? So this is the conjecture that we are doing, okay? Let me write down this as conjecture. Now, a conjecture must be proved, okay? How can we prove the conjecture? So let me prove this. Let me copy this here, and we will be using now the principle of induction for proving this conjecture, okay? So let me change color. Let me use the green and say that this proof by induction. Now we know that the proof by induction is made of two steps, okay? So we have the base step, which is basically proving the statement for an initial value. Now, in our situation, so the coefficient will be something which will have at the denominator 3 factorial Let's see what we get at the numerator. That will be f3. So k is equal to 3. But if k is equal to 3, minus 1, raise it to the 3 plus 1, of course, is going to be plus. So you see that the signs alternate. So we can immediately realize that the signs of every terms are minus, plus, minus, plus. So this is an easy way of finding that. For the final formula, which is the power of 1 plus x with the real exponent alpha. Remember that this formula is 1 plus alpha x plus alpha times alpha minus 1 divided by 2 factorial x to the square plus uh, the coefficient of x to the cube. It will have 3 factorial at the denominator, and there will be alpha minus 1, alpha minus 2, which is a little bit of a reminder of Newton's binomial formula, right? However, the difference is that now alpha is real, is not an integer. Okay, we will not provide the proof of this now. This will be given later. We need additional tools. What we want to do is just give a specific